Today, let me give you, I'm missing a few. Well, anyway, I think we have 2, 4, 6, 8, 9. I want to tell you, I posted some problems, and I also put a slide set that I was mentioning before that Tom Denny's name he created. I'm going to be using that to talk about the distribution function and probability density function after we do finish this part of the chapter 2. Then we'll get into combinational stuff in chapter 3. But right now, I wanted what I felt, because I've given you problems, and I feel that doing some of the problems would be very useful, especially talking about how to do them, and like your mindset on. And then I'll go through the actual problems that I put up there, and really the presentation. I may pull up the PDF of the distribution function. So before I start, any questions before I continue? Because what I plan to do is do problem 2.6 first. And this is one we didn't get at, but all these problems are they're related, and either to base theorem or to the, I call it the fundamental law of probability. But for 2.6, is there a wastebasket back there? There used to be. Can you check outside that door and see if there's one? Cause
there's one next to someone's office, I know.
Just grab
Wait,
it.
is there one in the corner?
I don't know.
No, behind the...
No, nothing back here. There usually is, though. Somebody stole the wastepaper. Thank you. Don't worry. There's plenty of these things.
Oh yeah, there was one there, remember?
Yeah, I have a feeling you got put outside and throw it. Okay. These markers only fits, but this one seems to work. No, not so good. No. Yes. All right, so problem 2.6, can you go ahead and give me the gist of it?
Yeah, 250 books.
So the total number of books equals 250.
100 of those books are history books.
So 100 history,
80 are science.
80
90 are other. And 20 of them are both both science
history and science. All right. Now I'm going to do a Venn on this one because it makes sense. And this one, if you did a Venn diagram, it should make perfect sense. How many tried this problem? Almost every. Did you try it?
I looked at it.
This is a kind of a classic problem in a lot of ways. It really showcases the benefits of doing a Venn diagram. So what I'm going to do is have this as my set of all books, which would be 250. And then this is history, and this is science. This is the overlap of science intersecting history. And then we have other too. And you know the actual numbers because they're there, but this is a pretty good representation of what's going on. And to be frank about it, I could just as well as get rid of this and say everything outside those is other, because that is the total set of space. I mean, all possible values. You all with me? All possible books. So now he goes through and he says, he's asking questions. First question?
It wants the probability of H given S.
Of H given S. So it's the probability of the history book given a science book is selected, right? Now, if you remember how to do this, first it's going to be the probability of what? History intersecting with science. Now in his book, he'll just have P of SH. He won't put that intersection sign. In Cooper and Macmillan and some of the other texts that I've referenced, they always use the intersection sign. You all with me, class, on this one? it's that, and then it's divided by what?
S.
The probability of S, or a science book. Now, what I'm really doing is this, and I've mentioned this before, but I'm saying, if the probability of a science book given, so this has occurred. Now, what's the probability of this slice? And I'm trying to do it with area, because each of the books is equally likely to be selected. Do you all follow me? And really, you can see it's this area, or the probability of that area, S intersect H over really S in terms of numbers. So here, this is 20, right? By definition, 20 books are both science and history. And then, if you look at the number of science books, it's 80. So this would be 1/4. I believe it's correct. You all with me on this? This is pretty straightforward one. It can get real complicated though. Part B is
H given S bar.
what's that?
H, probability of H given S bar.
All right. Now, if you think about this, we could use De Morgan's laws for some of this, right? But really, what are we talking about? This is the probability of history intersecting with science bar, anything that isn't science, divided by probability of science bar. I hope everybody follows me on this. And if you look at this, I'm going to try this with this. There's a couple ways to write this. So, who do you want? Others just outside. So if you take a look at this, well, we know where history is. And the intersection of history and science bar is interesting. So here's science, right there. Everything outside of science would be S bar. I hope you follow me. I'm trying to just make it clear with the pictures. With me on this, class? So if we look at the intersection, and actually, I'm sorry, I didn't put it here, but it's this too. That's everything that isn't science. You all with me? So he says that he wants the probability of a history book given that S bar is selected, right? Now, if you take a look at this, S bar is everything that isn't science. So the number of, you should say, S bar would be, since if you take a look at this, we have 250 books, 80 of them are science, so this would be 250 minus 80. You all agree with that? All right. Now, if you look, since that's the total number of S bar, the number of books that intersect history and S bar is this number, right? That I'm trying to show you right here. So that's really going to be simply, you could say it's H intersect S bar, that number minus the number of history books. Does that make sense? You can do it that way. So if we do this, we're going to have for what's on the bottom, S bar. And, you know, one of the things I'm not doing, and I probably should be, technically this probability would be this over the number 250, and it would be 80 over 250 as well. But the 250 will cancel because it occurs in the denominator of top and bottom. Y'all with me, class? All right, so down here, I won't even bother with that 250. HS bar is going to be this 100, right? And then it's minus the 20 that's going to be where the intersect is from last problem. And S bar is going to be 250 minus 80, right? And what's that going to be? So that's going to be 80 over, really 250, 25 minus.
170.
And I don't know, what is that? 8/17 is,
8/17.
what is that?
8/17. Oh, that's, it just shows it as 8/17.
Okay. So that would be part B, but you all follow me on this? De Morgan's laws allow us, we could play with this stuff, but it's my own opinion. If I can see what's going on visually here, I'll just not even mess with it, I'll just do it that way. I hope you understand what I'm talking about. Part C,
Well, that was the second.
That was
Thing
the
of
second
part
part,
A.
A.
what? Oh,
Part B is show the probability of H can be calculated using the law of total probability.
oh, the probability of H? All right.
Yeah, using
So-
LTP.
Let's do it right here. So probability of H is gonna be what? Probability of H given S, right? Times probability of S plus probability of H given S bar times probability of S bar. You all agree with that?
Yeah.
And if we're gonna do this, what is it gonna be? Probability of H given a science book. It's 1/4 over 250, but I haven't been putting the 250 in. Y'all follow me on this? I could, right? So this is gonna be 1/4, no cancel, times probability of a science is, where is it? 80, correct, class? Hold it, hold it, please. Let me do it this way. Probably H given S, the intersecting area is, I'm sorry. So that's from probability of H given S is this area divided by S total, I'm sorry. So that's going to be equal to 20, trying to write this down formally, divided by science is 80. And then it's probability of a science. So science itself, this is, I have to use the right numbers here. It's going to be 80, right, over 250. Correct, class? We're just making sure I didn't do something wrong. Then it's plus the probability of S, or of H given S bar. And we've got that right there, which is 8/17. Correct, class? And then it's times probability of S bar, and that boils down to what? That's really 170 over 250, correct? I believe. So you can see what I end up getting is that's 2 over 25 plus, and it's going to be 8 over 25, so that's going to be 10 over 25, and I believe that's right. Can you confirm that?
2/5.
Pardon me? Yeah,
Yeah.
if you, 2/5, that's right. So it's the probability of H. Now what did they want? Probability of S, is that?
No, that was it.
That was a bit.
I mean, I guess I think they were confirmed because you can find the probability of H directly, but they were just confirming that using LTP it got the same answer. I'm pretty sure.
So, I mean, why don't we do probability of H? So if you wanted to do it with the law of total probability, remember, there's other possibilities besides just S or H. There's other, but if we were to do this, what would it be?
100 over 250.
Well, but let me just write it out. So it's going to be what? Probability of science given history times probability of history, if we wanted to do it that way, plus probability of science given H bar times probability of H bar, correct? I'm just using the law of total probability. So what do we get for this? Probability of S given H is 1/4 up there, right? So that's 1/4. Now, and the probability of H
S
is,
given H.
pardon me?
We have a H given S.
This right here, probability of S, right? Isn't that probability of S given H times probability of H?
Okay.
Yeah, you all follow
I think
me?
he's just showing that plus 250.
You're right. No, he's right. But, and then, go ahead, say what you're gonna say.
Oh, I think I'm just confused because you said probability of S given H equals 1/4. That was H given S.
Oh, I'm sorry. My bad. Sorry. B. It's 8/17.
Okay.
I'm very sorry about that. I'm very sorry. You with me?
Yeah.
Anyway, so it's not my bad. Let's make sure it's correct. Thank you.
We've never done S given H.
Oh, yeah, that's new.
Oh, you're right. You're right. We gotta do it. I'm sorry about that. I was looking over here. Sorry, we might as well do it right now. Thank you very much. All right, so the probability of S given H, sorry. Take a look at it. What's it going to be? Probability of S given H. So really, I probably should erase this, but try to be clear about this, and sometimes I'm being too casual. Maybe we should do this. Here's science. Here's history. And here's other outside, total of 250. So if we want the probability of S given H is given. And now we want the areal ratio of that dark purple to that crosshatch purple. So this is 20 by definition. And the total of H,
100.
did I erase, is 100, right? So that's 1/5, is that right?
Yeah.
All right, let me see if I can do this now. So probability of S given H, or 1/5, thank you. Then it's the probability of H, and that's 2/5, right?
Yeah.
Plus, then it's probability of S given H bar. So for this one, this is S given H bar.
Can you do a 1 minus 1/5 to get S equals H? S
Pardon?
H bar?
Well, you know that the probability of H bar union H is 1. So, yeah, you could. Do you all follow me what I'm saying? I'm just writing this out with the law of total probability,
Yeah.
just for the visual. But you can do it that way. So this is 1/5 times 2/5 times the probability of S given H bar. And if I look at this, when I have H bar, it's everything outside this, H bar is everything, so do this. H bar is basically all this. And the probability of S given H bar is this. So really, it's going to be the number of science books, did you say is 100?
No, history books is 100, science books is 80.
So it's going to be 80 minus 20, because there's 20 in the intersecting space, right?
Over 150.
And then it would be divided by the other, which is going to be, is that 170 or is it 150? Hold on.
Well, less H would be 150, right?
Okay, you're right. Let's see. So this is going to be 80, all right? And that's 80 minus 20, and that's over. Total science is 80, or is that's over 80. I'm sorry about that. What I'm trying to do is show you the ratio. If I take this, the probability of this occurring would be the number of science books is 80, but there's 20 in the intersecting space that I didn't show you there. So that would be 60, right? If I take that divided by the total science books is 80, you end up with this, and this should be 80 in the bottom. I hope I'm being clear about this one. And then I have to take it times the probability of H bar. Well, if that's H and total number of books in H, did you say it's 100?
H is 100, yeah.
All right, so it would be 250 minus 100 or 150. That's what you were getting at last time. So 100 over 150. And that, let's see what it comes down to. That's going to be 2/25, right? Right here, 2 over 25. And this is going to be 6 3/4 times, and this is going to be 2/3. So now I get 2 over 25 plus, and 1/2, and 1/2 is going to be, I'll just put it as 1/2. So that ends up as 2 plus 12.5 over 25. So that's 14.5 over 25. And that should be right. What did you get for that?
Well, should it be 3/5?
Well, if this is right, maybe I did this wrong. Let's see. 80 minus 20 is 60, right?
Yeah, but the bottom is should be like the sample set is H bar, right? So shouldn't it be 60
hold on.
over 150?
Pardon?
Like where you have 80 minus 20 over 80. Why did you put 80 on the bottom? Because I thought the sample set is 80. So if it's
So,
S,
so I'm looking at this right here.
Yeah.
Okay. Probability of S given H bar. All right.
Mhm.
H bar is everything that is an H. So it's the entire region, right?
yeah, 150.
But, sorry, you were right. It's my bad. So it's 150 outside there, right? If that is given, the probability of this, that's 80 minus 60, right? Divided by 150. I'm very sorry. That's what you're getting at, isn't it?
80 minus 20.
Or 80 minus 20, so it's going to be, you're right about that. And I'm not putting the 250 in there, by the way.
Because the sample set's less because it's
Right, so basically what I'm doing is find the intersecting area right there, or the intersection of that is going to be 80 minus 20 is 60, and then the total number outside of H is 150. I think that's what you meant to say, and you're absolutely right.
Yeah.
Okay, now I've still got to get the probability of H bar. Well, if H is going to be 100, right? So that leaves me 150 outside there, so that's 150 over 250. So, right. And 150 cancels. Let me see if I can do this now. Okay. So that's going to be 2 over 25. They should have the same denominator if I get this right. And that's going to be 6 over 25 plus 6 over 25, right? And that's going to be 8 over 25. And that should be probability, total probability of S. And I believe that's correct, isn't it?
What is it?
The probability of S.
Oh.
But, I mean, how else could you get that?
Um,
Just take a look at the number of books in S, right, which is 80 over 250. See, same thing.
okay. So I was wrong. The probability of S plus the probability of H doesn't equal 1.
No, because there's other.
That's right. Okay. That
All
makes
right,
sense.
but
Yeah.
it's the probability of H in union with with H bar has to be 1.
Okay.
Because everything that is H and everything that isn't H has to be 1.
Gotcha. Yeah. That makes
My
sense.
bad on not explaining that, but all right. Is there another part to that problem?
So we did S of H.
Say
No,
again?
probability. What is probability of S given H? Which we did. We did that. Show that H given to S and S given H are related by base theorem.
Okay, so what he's really saying is the probability of S given H times the probability of S, or times the probability of H right there, is equal to the probability of H given S times the probability of S. What he's saying is prove that or show that. Now, honestly, this is a useful thing to remember. I found that it reduces the complexity by a lot if you think about it. So let's just see this probability of H. Can you guys tell me? I can't see from the side. I want to
Probability of
2
H.
fifths.
H times
1/5.
probability of S given H.
1/5.
Okay. Now let's see if this is, in fact, the probability of H given S.
1/4 looks like.
Can you see it over there or not?
Yeah, 1/4. 20 over 80. 1/4.
And then probability of S.
80 over 250.
Or 8 over 25.
Or yeah.
All right, so here I'm going to get what, 225 over 25, and there I get 2 over 25. It works. That's just, I guess, increasing your confidence. Is there another part to this one?
That was it.
I think, very sorry, I'm a little, I need to have some coffee, a little more coffee, to stay on. But that's a good problem. That's the reason I really like this problem, because it showcases exactly how a Venn diagram can help you, if you, the imagery. 2, 8, I think I gave you, right?
Yeah.
Let me erase this and get this. A few other things. By the way, you mentioned it was supposed to rain today earlier.
Yeah, earlier, but it was just cloudy.
Is it supposed to rain anytime later today?
I don't think so.
I'm in Alabama. I never believe the weather report completely. I've had experiences when I'm jogging. Like only a 45-minute jog. And about 20 minutes into it, got real dark and stuff. By the time I got back, I was drenched from head to bone. There's a lot of uncertainty. They don't give the confidence in it that we'll talk about with these predictions.
Well, they believe that 60% Saturday and 40% Sunday equals 100%.
That's where you're getting your weather information.
These are people that didn't do really good in probability. You know, I'm kidding. All right, so 2, 8, right?
Yes.
Go ahead, give me that, please.
Small electronics manufacturer buys supplies from 2 suppliers, A and B. Each widget the manufacturer produces requires 2 parts from A and 1 part from B. Parts A fail randomly at a rate of 10%. Fail rate is 10%. Part B have a fail rate of 20%. Assume the parts fail independently. So, what is the probability all 3 parts work?
Think in terms of, I'm trying to, if you think about the way we did those link problems, it's pretty, that is very useful here. So if you think about, they want the probability of
All 3 working.
all 3 working, so they want the probability of all working. Now, if you think about this, since we have 3 parts, this is the way I like to come at these problems. If none of them work, that could happen. If the first part works, the second one doesn't. If the second one works, first one doesn't. And then you can say, if both the second and third part work, the first one doesn't. First one, 0, 0, and you know where I'm going with this. All right, 1 indicates work, and 0 fail. Right? Total of 8 possibilities. With me?
Yeah.
Now, this is one way to view this problem. We could do this with the law of total probability if we wanted to. But what I'm going to do is just talk my way through this one. We want the probability that there's no failures or all failures.
No
Three
fail.
parts work. Yeah, no failures. Yeah.
All right, that would be this. You agree with that?
So
Does
one
one work?
Oh, I'm
work.
sorry. Yes. All right. So if they all work, it's that one, right? All right. So just follow me on this one, because now these are the first part, second part, and third part are independent of each other. If one's working, that has no bearing on the other's working or not. So if I take a look at this, the probability of the first part working. Let me go from let's take A as parts 1 and 2, and B as part 3. So the probability of the first part selected working would be 1 minus 0.1. You agree with that?
Yeah.
All right, the probability of the second part working would be the same thing, or this. Matter of fact, yeah. So it'd be squared. Then the probability of the third part working would be 1 minus 0.2, correct?
Yeah.
If you think about that, this is going to be 0.9, so it's 0.9 squared, and this is times 0.8. So that's what, 0.81 times 0.8. And I don't know exactly what that is, but
0.648.
0.648, is that correct?
Yes.
But you understand the method I used?
Yeah.
I'm gonna tell you, these kind of things are useful. We can write down probability, we can write down a lot of different ideas, but I think this is sound, the easiest way to do this, in my opinion. What's the next part?
What is the probability at least 2 of the 3 parts in the selected widget work? So
Okay.
two parts work.
You know what I'm up to now? 2 parts working. And I on purpose put this up here. Where are 2 parts working? One is work here. No.
That's not working.
Yeah, well, they don't usually work very well. But- go with this. So here's 2 working. And I should say this is 1, 2, and 3. And these 2 are from A. And this is from B. Just the way I'm doing it. Here's 2 working. Here's 2 working. And here's 2 working. I think you all see this. Did you all do this problem? I'm trying to do it and just talk my way through. If there's a question, please ask. So if I'm going to do this correctly, think about this. Well, this is not working, right? So, and that's the first thing. So for, at least for this one right here, let me call this A, B, C, and D. All right, for A, I'm going to end up getting what? That's going to be probability of it not working is probability of failure is 0.1. Y'all agree with that? Then the probability of this working would be 1 minus 0.1. Agree, everyone? And the probability of this working would be 1 minus 0.2. So you end up with 0.1. You're going to see that we're going to multiply this. Let's see here. Well, let me just write it down. So we got, I'll tell you what, let me get that, and then at the end, for part B, right here, is this one, right? And that's the probability of the first one working, which is going to be 1 minus 0.1. Probability of the second one not working, which is 0.1. And probability of the third one working, which is 1 minus 0.2. For C here, all right, now you got the first 2 working are 1 minus 0.1 squared, and the second one not working for 0.2. And then for D, wait a second. Yeah, for D, I'm going to have all of them working, so that's going to be 1 minus 0.1 squared times 1 minus 0.2. And we have to sum all these up. Do you agree with this, class? Just the way I'm doing it? It's simple, and I'm not trying to make it complicated. For this one, the total then is going to be, let's see, how many of these are the same? All right, these 2 are the same, right? So I get 2 times 0.1, and this is going to be times 0.9. I'm taking a look at this right here. And then it's going to be 0.8 here, plus, and then for this one, it's going to be 0.9 squared times 0.2. And for this one, it's 0.9 squared times 0.8. When you add those up, plus this, can you tell me what you get? There's probably a quick way to do this. I've got 0.9 squared here, 0.9 squared, and we've got 0.2 plus 0.8, which is going to end up being 1, so that's 0.9 squared. 0.9 squared is going to be equal to 0.81. And the first one, let's see, what do we get for that? 0.72 times 2 is 0.144. Is that right? So what does it come down to when you do this?
I got 0.954.
0.954?
Yeah.
Is that the answer?
95%.
Well, it's, okay, a little bit better, but close.
Yeah.
All right. Anyway, that's that one. What's the next part of this? It's kind of an interesting problem.
Given the widget has one failed part, what is the probability that failed part came from A? And then what is the probability that failed part came from B?
Okay, so here, there's the probability. Oh, okay. So, okay. I'm going to try to say this clearly. So, you've got this widget made up of 3 things, and they want the probability of what?
The failed part is coming from A,
Okay.
so there's one failed part. What is the probability that failed part came from A?
But there is one failed part.
That's the given.
Okay.
And then
Let me go back to this. Zero is fail. 1 is so. I'm just drawing a binary scheme. So, given that there's one failed part, and if I take a look at this, failure is 0. So there has to be only one failed part, or one or more.
just one failed part.
It didn't specify, but in the answer it's exactly one.
All right, if you've got one failed part, here's one possibility, right? Then here's another possibility.
Of those are working.
Oh, I'm sorry. This is, sorry. So 0 is failed. One failed part would be 1, 0, and that would be here. Right? And 1, 0 would be here. And this is 1, 0. So if it's not one, or sorry, only one failed part.
Yeah.
That's the assumption. So I'm looking for the ones with 0. There are 3 of them, right? So if you take a look at this, the probability of this one is going to be, and 0 is a failure, is 0.1 times 0.9 times 0.8. That would be the probability of that one star. I think you all follow me what I'm trying to do. The probability of this one right here
Same thing.
is going to be, well, is it? Let's see. Yeah. So I can multiply this by 2. So I'm just going to say that. And finally, this one is going to be 0.1. Oh, I'm sorry.
0.9 squared.
Yeah. And
2.
So when you add those up, that's the probability of having just one failed part. And I don't know exactly what that is, but this is the number of one failed part.
And the question then what's the probability of like that part either being A or that part or even or B?
Right, and we're about to do it. So if you look at this, there are three possibilities, here, here, and here. So they want the probability of the failed part coming from A, right?
Yeah.
If you look at this, now we've got this probability, that means we would take, I don't know if I wanted to write this up in it's really gonna, it should be, I don't want to confuse you. So I would like to know the probability of a failed part coming from the first, or from A, given that I have just one failure.
Yes, exactly.
And if I
It
do
could only
this,
be 2 of them.
pardon?
It could only be 2 of them. It could only be the top one and then the middle one, right?
Well, yeah, this has a failure in the first, in bin A, this has a failure in A, and this has a failure in B. So if you think about this, the probability of failed part in A, given this is the probability of all failed parts, you can do that with a simple ratio.
Yeah.
And I'm going to try to write this out. And I'm not sure how he actually shows this, but the probability of I'll just spell failure in A given one failed part. This is like, I'm trying to do this P of A given B times probability of B equals probability of B given A. Actually, you can do it, no, sorry, we can do it with the law of total probability. We don't need this one, but I'm going to try to talk my way through this, but we could use the law of total probability. So the probability of failed part coming from A is going to be given, oh, there is one failed part, would be the probability of this occurring plus the probability of, I'm sorry, failure, yeah, probability of this occurring plus the probability of this occurring, and then we have to divide that by the probability of all of this, of this, and this. The ratioing way is what I'm trying to show you, but I'm not saying it as well as I like to. So anyway, for this answer, the probability of failure occurring in A, over assuming one failure, that's going to be 2 times 0.1 times 0.9 times 0.8 over, and the sum of those three, I don't even know if we calculate that, but what's the sum of the two? It's really that plus last part, 2 times 0.1, 0.9, 0.8 plus, and then it's going to be 0.9 squared times 0.2. And what does that come down to? You could have
That bottom part is 0.306.
all right,
And the top one is 0.144.
0.144.
Yeah.
What is that then?
0.47.
Is that the right answer?
Yeah.
Well, it is. You all follow me on this? I'm trying to write this out with the probability of A given B, but honestly, it seems to get a little busy in terms of how we define that failure. We'd have to define like the failure occurring in A given only one failed part times that. But I think you can get it from here. I like these things, but I'll let you know. Did he do this or not?
Any solutions?
Did he use this type of an identifier?
Well, he doesn't show that. He just writes. I'm pretty sure he just writes that. But we have on the left.
But it's important that you see how you got it.
He doesn't.
I wish he would have wrote that.
I mean, this right here is very useful.
Yeah, I know. He just writes the answer.
Wow.
So it's like.
The answer sometimes is not as helpful as a method. All right, I wanted to talk about that. Is there another part to this or not?
Yeah, so you do the same thing for, what's the failure of part B failing? Like the,
Probability.
so,
Wait, say it.
So the failure in B. So we did the failure in A.
Okay,
the second
given
part.
there's one failure?
Yeah, same thing, but it's just failure in B.
All right.
So could you just do 1 minus 147? You could?
All right, now here's why. Look, what's the probability that all, I mean, if these three things occur, what's the probability that all three things occur? One.
Yeah.
All right, so if the probability, remember, it's assuming these occur. That's
That's
the
the
given, right? So if those are given, the probability that this occurs right here is just what? 1 minus the probability of the last one. And that should be the right answer, let's see. So it's going to be 1 minus the probability of, what was our answer again?
0.47.
0.47, so that's 0.53. Is that the answer?
Yeah.
Okay, but that would make, I hope it makes sense to you.
Yeah.
And I'll tell you where I can see myself struggling, is trying to, I mean, I struggle this way when I'm trying to explain this. If I put down like a Venn diagram of this, the actual probability of this, I have to define what I mean by a new event, call it D or something, is the probability of like just one failure, and then the probability of failure in A, and then you have to do that conditional business. Okay. I won't spend that much time, but I think it's good. I want to go through next. I mean, is there another part to that problem?
Yeah.
Well, go ahead.
given the widget has two failed parts, what is the probability both failed from parts came from A?
Why don't we just do it, guys? By this time, I think you pick up on it. All right. I'm pretty sure you see it. All right. Here's the possibilities. 0 through 8 in terms of the possibilities. He says 2 failed parts?
Yep.
All right. At least or
Has two.
only 2. 2 and only 2. All right, so here's one of them, right? Here's one. There's two. I'm looking for 2 zeros. Here's another. If I take a look at this, here's another. And here's another.
No. 2
Pardon?
zeros.
2 zeros.
2 zeros.
Oh, sorry. You're right.
So it's just the 3.
Okay, just 3. Right? So he wants the probability set again?
Here's the probability that both failures are from A.
All right. Now, if you look at this, by the way I did it, I think it's straightforward. This has both failures in A. There's this, and this. That's the only possibility that both failures in A, right? So if I find the probability of this occurring, and this occurring, and I want the probability, given that the two failures, that both failures occurred in A, to be this probability over the sum of this probability plus this probability plus this probability. Follow me on this, class? So let's go ahead and just do this. This one right here is going to be 1 minus 0.1. Well, I'll put it as 0.9. Might as well just this, because this is going to. This one right here is going to be 0.9 squared, and then it's or I'm sorry, 0.1. I'm not doing this on purpose, trust me. Times, and this is going to be 0.8, and that's this one right here. This one is going to be 0.9 times 0.1, I'm doing this one, and this is going to be 0.2, right?
2 times that.
And let's see. Yeah, that's right. I think so. Y'all-
Plus the top one. Oh, you're not bad, you're not doing the total yet, right?
It's this one and this one. I've added right here. Okay, so if you take a look at that, that's the total, so it's 0.1 squared times 0.8 plus 2 times 0.9, 0.1, 0.2, and we have to divide that into this one, which is, you might as well tell me what you get.
They're at 0.18.
What do you get for this? Did you actually do it or just?
Yeah.
0.8?
0.18.
All right, 1.8, is that the right answer?
Yeah. Yes. Yes.
I prefer always showing the possibilities with these kind of problems. Until you get better at doing all right. Okay, I think, is that it?
Yeah, there's the
All right, what I want to do is the link problems, but I want to, I'm going to show you this stuff because we'll talk about the binary channel again, but really it's the binary channel, and the more I looked at it, the more obvious it was. The only thing we have to do is find the probability of x being 1 given y is 1, then the probability of x being 0 given y is 1. And if the probability of x equals 1 given y is 1 is greater than the probability of x equals 0 given y is 1, then we assume x is 1. That's the only thing we're saying with that, out of that a priori business in the max or the math rule. The drug testing is similar to the actual binary channel. I want to get to, not that one, but I want to get to this part, and this is the diamond network, and this is on page 40. Now the diamond network is the last, we'll go through a few more problems, but this is the last one we have to do. I know I'm running a little on time, but
Do we have the quiz started?
we are. But this is going to be real quick. So for a diamond network, I'm going to assume this. Here's a sender, here's destination. I'm going to assume all these links have a probability of working of P. All of them have the same. They don't have to, right? Now, here's the way he suggests doing it, and I kind of like this. He says the real issue is this middle part. So that one can be on or it can be off. Do you agree with this? So let's assume, and I'll just call this P middle. So, and this is the probability of it working. So if P middle is 0, it's not working. If you look at that, then you have this. From the sender to the receiver, you have this. This is going to have a probability of working P. This is P. Then you have another link here, probability of P, and another probability of P. And we want the probability of this working. In other words, of either this link or both links working, right? So it's 1 minus the probability of both of those links not working. You all follow me? Just hold on.
Can you repeat that?
Yeah. Let me do it this way. Do you remember these problems where we have anything in series where that's the probability of it working? I can get rid of those two links and replace it with just P squared if they're the same. If they were different, they would have to multiply P1 times P2. Do you all agree with that? Down here, I can do P squared as well. Now again, if there were different probabilities, then it would be P3 times P4, correct? If I take a look at this, the probability of this not working is 1 minus this. The probability of this not working is 1 minus this. Do you agree?
Yeah.
This is going back to what we did before. So the probability of this system not working would be 1 minus P squared squared. That's the probability of it not working, so the probability of it working would be 1 minus that. So this is the probability of this working. And I'll call this P. S goes to D, given P middle equals 0, not working. You all follow me? Remember, I pulled out the middle link, it's not working. Now the next part. Now let's say the middle one's working right here. So if the middle one's working, this is shorted from here to here. So then you have this. And this is the center here, and this is the destination. You have this. I hope you see what I'm trying to do. That's just the way they put this. This is P middle equals 1. It's working. If you take a look at this, this is P working, P working, P working, P working. You're going to see this in a second. I'm just giving you some. Y'all with me?
Yeah.
So the way we go about it is we're going to find the probability of this not working, 1 minus P. The probability of this one not working, 1 minus P, right? I can say this link can be replaced by something, or the probability of this first link not working is 1 minus P squared. And if I subtract that from 1, 1 minus P squared, that's the probability of it working from here to here. Take a moment. Do you agree with that?
Yeah.
Can you see it's exactly symmetric from here to here? They're identical because I made the probabilities all the same. You all see that? So just what? Take this and square it. And that's the probability of senders to destination working given that the middle leg is on, or given P middle equal 1. So that means the probability, that diamond network there, the probability of the sender to destination working, this would be working now. I'm not writing it all down, but y'all follow me on this? It's going to be equal to this probability. So it's 1 minus P squared times the probability of the middle one not working, which would be 1 minus P middle. Now, if P middle is the same, you all see how you're going to have 1 minus P cubed? You with me? That's the first one not working. It's going to be plus, and now it's the probability of this configuration occurring, and that's 1 minus, boy, this is a fun one to do it. It's going to be 1 minus P squared, and now I have to multiply that by 1 minus PM. Now if PM is equal to P, which it is in this problem in the book, you can find this value very quickly. Do you all agree with this, class? Did anybody look through that problem? If you'll notice, the big thing is, the way he does it, is break it down into 2 parts. One where the middle leg is working, one where the middle leg isn't working, and find the actual probability of the center to destination occurring for each of them, and then combining the 2 with the weighted probability the middle is working or not working. Did you have a question?
Yeah, could you explain how you got the first part of the answer? So
Wait, here?
yeah, so when the middle is not working, the
Here.
probability is 1 minus P squared, but then
Hold on. Let's go back to it. Take a look at this for 1 second. This is what we're talking about. We just want to figure out the likelihood of center to destination working for this. With me on this?
yeah, we got the probability there. Yeah.
All right, so this is just P squared up top, P squared in the bottom. Probability of it not working, 1 minus P squared on top, 1 minus P squared in the bottom.
Sure.
Probability of that occurring, probability of this one, 1 minus P squared times probability, 1 minus P squared, 1 minus P squared squared.
Yeah.
That's this. Right? Now it's times the probability of the middle one not working. If it was working, it would be PM, right?
Mm-hmm.
If it's not working, it's 1 minus PM. That's this middle one I just took out. With me?
Got you.
Now, this one has the middle one working. So now you got these 2 in parallel, these 2 in parallel, same type of problem, only instead of having 1 minus p squared, you have 1 minus p, 1 minus p, 1 minus p squared. We have to subtract that from 1. 1 minus p squared. Probability of this working, they're identical, so just square that. And then, that's it. Think about it. Does it make sense?
Yeah.
And I'm going to give you a quiz. I got to spend my time. I